Okay. Hi. So I'm going to talk about kind of a model framework that I developed over the last 10 years. So I'm going to emphasize three ingredients, but there's actually a lot of small things in this model that make it very numerically efficient. And I use it to simulate the continuum from coastal morphodynamics to, as you will see, the river morphodynamics going to deltas, barrier island, estuaries, and so forth. So this is just a very short list of some of the things that are in there. Mostly we'll have river hydrodynamic, tidal hydrodynamic, waves, transport of sand, silt and clay, bank erosion, vegetation processes. So I'm going to emphasize in red how I did those in a kind of a smart way. For the first two, for the hydrodynamic, the key for me was to make it a steady state, because mostly then you don't have to worry about hydrodynamic instabilities. And so let's go more into the details of it. So if you look at the 2D shallow water equation, first you make it at steady state. And then I decided to remove the advection of momentum. That's because to make the problem much simpler. And I'll discuss what are the limitations of doing that. Now, mostly you can recast these as a nonlinear Laplace equation, which again is already steady state, is an elliptic equation, so it's very stable. But now that coefficient is nonlinear because h depends on eta, which is your unknown, and then there is also the nonlinearity with the one of the velocity in the friction. But I just solved that iteratively. So because when the diffusivity is constant, and it's very easy to solve it, it's very stable, and I just do iteratively. Okay, so let's go into some comparison. How does the hydrodynamic changes if you include the advection of momentum, which is kind of the standard way of doing it, or if you remove it? So this is a comparison using the hydrodynamic of del3D on a delta bathymetry generated with the del3D. So on the left is kind of the standard approach, and you get mostly the jets at the end of the channels. So in del3D, if you remove the advection of momentum, the flow doesn't capture these jets here at the end of the channels, but within the delta is very, very similar. You can almost tell the difference. And actually, quoting a very paper from last year from Nicolas, mostly the inertial model, which is the model without the advections, works very well when you already have channels, mostly because the conservation of mass dominates the flow, and then you get very, even neglecting the advection momentum, it works very well. And then the bottom is the velocity, and the top is the water level. And again, you are very, very close. Within the delta is like within 1%. Now, for comparison, the one on the right is the hydrodynamic calculated with my model. So it's the same equation, but solved with the different numerics. So the middle one is kind of run with the del3D codes, which I don't know what numerics it does. But on the right is the nonlinear Laplace equation iterated. And again, they are very, very similar. There might be a little differences because I think in del3D, there is also the eddy diffusivity of momentum, which I don't have it in mind, but it's kind of a minor effect. Within kind of the channels, the flow is very, very similar. Okay, so what is the consequences for morphodynamics in neglecting this advection of momentum? So this is two morphodynamic simulation run with del3D. The top one is the standard way of doing it, and the bottom one is without the advection of momentum. And you'll see that without the advection of momentum, you don't form the initial channel here, because mostly the flow doesn't have this inertia, so it doesn't want to incise at the beginning in the right location. But so you kind of get more of a shield. But as the delta develop, then the channelization becomes the dominant factor determining where the water goes, and the deltas look very similar. And again, there are also the channels keep changing, so they're never going to look exactly the same. But even without the advection of momentum, you will see that you form these kind of channels at the end that looks like there is a jet, but there is actually no jet. So the morphodynamic dominates over kind of the hydrodynamic. And actually, going back to Nicolas, so he has also a model with and without the advection of momentum. He actually solved it unsteady. So it's unsteady flow on the right without the advectional momentum, and here is a comparison on a braided river with different kind of settings on each row, but mostly they are very, very similar. And in most circumstances, he also argued that it works very well with the advectional momentum. Okay, so that was for the hydrodynamic. Now, the second ingredient was for the sediment transport. So let's pick a total transport capacity predictor, like Engelund answered. So I use the star to define the capacity. Then you have the Exner equation with this QS. Now, in most models, kind of assume that the transport is at equilibrium, so the transport capacity is the same as kind of the actual transport. But if you relax that, and you mostly assume that it's not at equilibrium, which is the same as calculating as a suspended transport, where the erosion term is recast of this transport capacity. Then mostly I show that is the same as setting that the total transport is a convolution of the transport capacity. Mostly the transport at one location is kind of taking a weight of the transport capacity behind it. So these two are mathematically equivalent when you discretize it. And the thing is that if you imagine that now your transport is more at one location, depends more, it's kind of a weighted average of the one behind it, the gradients are going to be smaller in the transport. The transport field is going to be more uniform. So the gradients are smaller, so you have less kind of perturbation in the bed when you do the divergence. So it's more numerically stable, meaning you can have larger morphodynamic time step. Now the question is, how does the morphodynamic change when you do an equilibrium versus non-equilibrium? Like, is it that different in doing this two-way, considering the total transport being the total transport capacity being the same? So this is, with my model, kind of a morphodynamic simulation, and mostly the bottom one is assuming that is at equilibrium, which actually you can do that by using the suspended sediment transport and setting the settling velocity very, very large, so mostly the transport instantaneously adjusts to the local condition. So you get the bottom one, and then the top one is kind of the reference value with the realistic settling velocity for sand. And you can see that they are very, very similar. Now, they're not exactly the same. The channels, maybe these are maybe a little more in size than this one, but big order, first order, they're almost identical. So the point is, doing it non-equilibrium is not so much to make it better or more realistic, it's just more stable. That's why I do it. So I can do very large morphodynamic steps. So that's kind of the second trick. The third trick is kind of how you do bank erosion, and more generally, how I do the transverse transport of sediment. So mostly I add this diffusive term, which depends on the slope of the bed, and then mostly the magnitude depends on the transport at that cell. And I apply that everywhere, even at the interface between dry cell and wet cell. So actually, in my model, there are technically not any dry cell. There are just cells with very, very small water depth. And so you erode this bank by making kind of a diffusion process between these two cells. But the trick is to kind of calculate the diffusivity between these two cells. You use the value of the downstream cell. So somehow you're parameterizing the flow here, impinging on the wall and making everything kind of, instead of eroding, I make it sloping down. And again, this is very numerically efficient, and you just do diffusion implicitly, which again makes it very, very stable. Okay? You can talk to me about the details later. I just want to show cool videos that I can do with this model. So this is just a kind of sensitivity analysis. So this is kind of a standard delta with just river and sand, and changing the downslope transport. So how much this, mostly with more downslope transport, you want to make channels that are wide and shallow. And this is kind of a smaller downslope transport. And here, so I forgot to mention, with the bank, you want to erode the bank a lot with this mechanism. So you can put kind of a coefficient that makes the bank less erodable. It's kind of the break in your model to simulate like cohesion with mud and vegetation. So here, if this bank erosion, I put it to 0, which is mostly removing the downslope transport of dry bank, then you get much narrower channels, kind of more like bird-foody, like the bird-foot delta in the Mississippi. Okay, so this is just the video. I already hope it runs. Yes, so this is just the video of those simulation. You can kind of see how dynamic they are. You can kind of see the channels avulsing. And this kind of probably looks very similar to what you already get using either Delft3D or Delta RCM, which are kind of other available delta evolution models. Again, for comparison, this is also very fast. So each simulation is probably 10 minutes to run on your desktop with one core. Now here we go to the good stuff. It's kind of applying this to more complex scenario. So here I'm trying to hindcast the evolution of the Walks Lake Delta in Louisiana. So this is kind of the initial bay. This is where the delta kind of started. Now here, in addition to the river, I also had tidal flow, sea waves, swell waves, and I transport sand, silt, and clay. And then I also have vegetation that kind of affect the hydrodynamic and also makes organic accretion. So this is the bathymetry. This is a transect, kind of roughly this kind of crossing this way. And so this is the sand and mud composition. So sand is going to be yellow, mud is going to be black. And this is silt and clay, where red is clay and blue is going to be silt. Okay, so this is evolving over 80 years. And I don't know if you're aware of the shape of the Walks Lake Delta, but it kind of looks similar. Here you can see, for example, there is sand in the channels, but more mud in the island. And actually, if you look at what is in the island, there is mostly silt. All the clay kind of gets washed away. There is only clay trap here where you start having vegetation. Now, this is actually how the topobathymetry of the Walks Lake Delta look like about in the last 10 years, because it's actually a collage of different data sets. And this is the last 20 years of evolution of my model. You can kind of see that, you know, it looks relatively similar, both the size and the shape of the channels, the width to depth, kind of the details of the tip. There is a pretty good match. I need to do it quantitatively, but at least kind of visually, they look pretty close. And they also match the timing. This is exactly, you know, it started in 1940 when you open it, and this is when what it looks like at exactly the time where I'm comparing with the topobathymetry. So continuing on Louisiana, this is the kind of the bird foot. So here now we have 80 by 100 kilometers domain. This is a little more kind of an idealized hindcast of what the bird foot delta might have done. So for reference, these delta form in the last 500 years, the last tip of the delta. So this is the time. So the first number is a number of years of evolution. So I'm going to run it for about 100 years. So here you have the same ingredient as the Walks Lake Delta, just larger discharge, larger sediment concentration, because, you know, a few hundred years ago, the Mississippi actually transported more sediment. And you can kind of see this long channel sticking out onto the continental shelf. And notice, for example, here is mostly sand in the channel bed and mostly mud all the way outside. There is also waves acting from the offshore, and you can actually see start to forming shoals here. So these are actually kind of crevasses that are forming and delivering sediment laterally, while most of the flow kind of goes in the main channel. And again, you can see constantly working on the front when maybe the channels get abandoned. So here is actually going to make a major avulsion and go this way. And now this part is mostly abandoned. It gets reworked by waves. And you can actually see here there is the front. Most of the shore face is sandy and everything else is muddy. And also here you can see that on the lower on the continental shelf is mostly clay, and the part that is more shallow, maybe 5 meters or so, is more silty. And actually, recently I found out that doing the 2 classes of mud was very important to get this muddy system correctly. Now, talking about Murray Island, the model can also do barrier dynamics. So this is a simulation inspired by the Virginia Barrier Islands. So this is now a continental shelf with only sand, no mud and vegetation. And this is kind of simulating the barrier roll over. And there are kind of storms happening. You can see kind of small breaching of the barrier islands, similar to kind of overwash, and the flood deltas kind of migrating landward, and the inlets opening and closing and migrating downdrift, and some of these barrier islands sometimes being obliterated, but then form more landward. So this is kind of the wave dynamic component. Well, this is wave and tide. The model, actually, one of the first few things I did was applying to kind of a marsh setting. So it's now there is a tidal flow, and on the kind of bay side, there are sea waves and edge erosion. And one of the things I added more recently was the meandering. So the way I do it is when I have the hydrodynamic and the flow is curved, there is kind of a correction of the flow to have faster flow on the outside, and then there is a correction to move sediment more in the inward side of the band, and there is another routine to also erode more the outside of the bank. You can see you get, even in tidal system, you get channel meandering, channel cut off, and then when they are abandoned, they get filled in. You can actually see these being present in real marshes. This is actually a marsh somewhere in the Chesapeake Bay, and actually the domain is inspired by, and the forcing is inspired by this setting. And actually there is also ponds that are formed in the marsh. Ponding is another mechanism than in the model, so ponds form, but then it can get reconnected as the channel move, and then they get filled in, and you can see ponds in also real marshes. Okay, so this is a marsh. This was only with the mud. Now, one of the things I really work on was to combine, do the simulation of marshes with the mud, so silt and clay and sand. I was really interested in recreating these. You run? Okay, recreating the sand dynamics near the inlets. So that area there on the right, is mostly sand, and these channels are. Okay, this stop. So that area is very dynamic. The channels keep migrating and kind of constantly rearranging those sandbars. And it was an interesting experiment of trying to recreate how a marsh forms, like in a whole estuary forms, because I always thought that it kind of forms from the outside or from the edges in. But actually, sometimes the marsh can form on these bars. So in the right condition, the bars are high enough, and then get colonized by vegetation, and then the mud kind of that get trapped, and that makes the progradation of the marsh very discontinuous. Again, you can have instances of these marsh islands forming up, and then the back part is more protected, and then you can kind of have a larger expansion of the marsh. So this is kind of create this very discontinuous creation of the marsh, even though the boundary conditions are stationary, so same sea level rise rate, same sediment supply. And actually, even in the real setting, you can see that there has been marshes being formed. So this one on the right, even recently. So those are like a few hundred years old marsh that form here. I just want to finish it because it's very pretty. And again, there is also still kind of channel migration, and perfect. Okay, so relatively good match. This is now applying to a bigger estuary like the Skelde. So this is just now with sand and tides, and I was really trying to get these big channels, and they are kind of a lateral migration and this formation of these ebb and flood channels. So the top one is the real bathymetry, and this is the bottom one is the one produced with the model. And again, it looks relatively similar. And interestingly, in the model, there is no asymmetry between ebb and flood. The hydrodynamics is actually perfectly symmetrical. All the asymmetry comes from the sediment transport. Yet, again, you can kind of spot areas that look like what is being classified ebb and flood channels, which is still kind of something I'm trying to figure it out, how it's possible to recreate these features without having flow asymmetry. But again, beautiful ebb delta formed there. And again, this very beautiful channel meandering. Now, since we're doing meandering in the model, why don't you put it also in the river part? So this is a simulation now of a braided river. So this is now river flow, but with the meandering, okay? So this is inspired by kind of a braided river in New Zealand. And there's also flow intermittency, so there's kind of high flow and low flow. And again, I think it looks relatively realistic. I really like that during high flow, the channels tend to smooth, and then during low flow, it kind of wants to meander a little because the channels are a little more incised. And again, this is like 30 years of morphodynamic. And again, this runs in a couple of hours on a single core. And so this is kind of braided dynamic. Now, if you also add, mostly I accrete, this is the last simulation I did very recently. So for floodplain here to cut corners, I just made an accretion rate, but I can simulate mud in my model, so I can do a real floodplain dynamic. So just mostly accrete the floodplain where the depth is very small by constant rate, and then make the bank less erodible. I should be able to make meandering. Yes, okay. Why doesn't that? Come on. Oh, that was the last video. I was very close to it. Audio S. Okay. Take off the laser. I'm wondering if I can do it from here.
Yeah, so with the laser pointer on.
Okay. Yep. No, I was trying to run it without the.
Right there. Hold on. It's right there. Might be.
No.
Trying to process it.
Can we run it without the presentation mode? Just run it.
Yep. It's right.
Okay, it's running.
Yeah.
Okay, perfect. Okay, let's just give it like. Okay, there it is. So yeah, kind of channel meandering, and of course you get cutoff and the filling of the abandoned channels. And you can see kind of deeper depth on the outside of the band, and again, relatively realistic. Again, more to be done, but it's, it can also do this kind of type of setting. So yeah, the whole continuum of river to coastal morphodynamic in a couple of hours on a single core. Well, I gotta tell the conclusion because the video still runs. There is a lot to test more in the model. I need to test more precisely how much is lost by neglecting the advectional momentum. I have some guesses of what processes will not be captured. For example, alternate bars might not be created as well. But again, as Nicolas suggested, all the things that are in more channelized dynamics, you shouldn't matter if you neglect the advectional momentum. And again, there's many scientific questions to be asked. I'm very interested in the role of waves and mud in delta dynamics. But for the river part, I'm sure you have more ideas of what to be done. What I would be interested in kind of testing my bank corrosion model with other more standard way of doing it. And finally, so the code is available. I'm very bad at commenting it right now. I'm the only developer of this. We try with Greg sometimes to translate some of the components into a LandLab. It is possible because fundamentally there is a diffusion equation that needs to be solved. But maybe now with the use of AI might be easier. And I think some of these modules can go into LandLab and kind of complement what is already there.
Very nice presentation. Thank you so much. Are there any I see a question way in the back there. Dylan.
So there is 3 ingredients into that, but mostly it's more emerging from there. So when the flow is curved, so you have the flow field, and then you kind of look at the curvature, and then you can kind of add the correction to kind of push the flow a little more on the outside. But you don't really specify, you don't really track a bend. You just look at the flow field, and then you apply this correction. So it's agnostic on what you're doing, on what, you don't tell that you are in a channel. So you have a flow field, you have this correction. Then once you have that correction, you also there is a correction for the sediment transport. But again, you don't need to tell we are in a band. You just have the flow field where it's curved. It will transport kind of in the inner part of the curved flow. And then there is another part where kind of on the outside of the curved flow, you add kind of, you further erode the stuff on the outside. But you don't really tell it's a bank. It's just you erode whatever is in that side. So you try to, it's more modifying the first principle of the flow, and then the meandering comes as a consequence. Okay, so the correction for the hydrodynamics. So this is kind of, I don't know how it's done in 2D models, but mostly for me, if I have a 2D flow, so I calculate the curvature, and then based on kind of the shape of the curve flow, I add the extra friction in the inner side of the flow, and then I recalculate the flow, just the flow field, not the water level, and then automatically it's gonna push the flow field more on the outside. And then for the inward transport, you kind of look at where the flow is curved, and then you add a little vector of, because all the sediments is transported in suspension, so you add, in that transport, you add a little vector into the inner side of the band, and then if there is sediments in suspension, it's gonna bring it more, deposit more into the inner band. It depends on the setting. So for the Barrier Island, it started with the simulation I started was it was mostly the flat shelf where the sea level was 100 meters below present, and it just kind of rose and just allow it to form the marshes. But sorry, the Barrier Islands. But you can start with the real bathymetry. Yes, you can. So for example, in the Walks Lake Delta, their bathymetry was actually very similar to what should have been in the 40s when the delta formed, because it was kind of a relatively flat bay with that kind of shoreline. I didn't show it here, but I can start the Birdfoot Delta. I have a simulation when it starts with the present day topobathymetry.